Okay, so welcome everyone to the joint seminar between GQFI and the Warsaw String Theory Group. Today we are very happy to have Pedro Jorge Martinez, that is now from some superposition caused by COVID between La Plata and Bariloche University. And today he's going to tell us about the modular Hamiltonian for holographic excited states. Please take it away.
Okay, well, thank you all for having me. I miss the Warsaw here on the bottom. I'm sorry for that. Thank you all for having me. As Powell just told, I just got my PhD from Universidad Nacional de La Plata in La Plata near Buenos Aires, and I was in quite asymptotic transition into a postdoc at Instituto Balseiro, which I am not yet able to reach, but I hope to reach it very soon, both with a scholarship from CONICET. Today I'm going to talk about this work we did with these collaborators, Raúl Arias, Marcelo Bota-Canchef, and Juan Zárate, on this work that appeared on Archive earlier this year, which is called Modular Hamiltonians for Holographic Excited States. So thank you again for having me. Let's begin. Let's start with a summary of what we will do. I will try to give first an introduction on the objects we're going to deal with, mainly modular Hamiltonians and a little bit of Tomita-Takesaki formalism. Then I'm going to describe as detailed as I can our setup. And when our setup is clear, I think our results will be also easy to understand, and why did we approach the problem in the way we did. Once the setup is clear, then we're going to revise what results did we get in the CFT side and what results did we get in the ADS side. And maybe the ADS side will allow us to do some more hard, I wouldn't say hard, but more fine computation. And then we're going to wrap it up with some conclusion. So if you only have like 10 minutes to hear, let me give you a punchline of at least my perspective of this work. There is this, I wrote there old, but maybe it's not old, but maybe well known, at least in the literature, that there is a map between something that I will call the TFT constraint, but let's say it's a TFT purification of a system in the TFT vacuum, and how it is related with the Tomita-Takesaki formalism and the modular Hamiltonian. Also for example, let's say a quantum Q theory vacuum. So if you have let's say a Rindler space and you have this purification, you have one side and the other, you can think of it as if you start with one side, you can think of the other side as a TFT purification of the system that are connected at x equals 0. And then you can map line by line this to a Tomita-Takesaki equation, S applied to phi, to a state, and so on. And you can go back and forth from these two formalisms. This is something very well known, and in this work, also by some similar collaborators, we ended up in a completely different setup, at least for us at that time. We were able to excite this TFT constraint, try to do some excitations, and still define an excited states in this TFT formalism, which still met a constraint similar to the excited state, that is a deformed constraint, but it is still very reminiscent of this vacuum constraint that I will describe. So then the question was somewhat more clear. It was, is there still a way to map this constraint, that excited constraint for excited states that we have found, into a Tomita-Takesaki problem? The main advantage of doing that, you could ask us why are we obsessed with mapping everything to Tomita-Takesaki, but I think that the main advantage of doing so is that if you meet the Tomita-Takesaki hypothesis of the theorem, and then you write something that looks like and behaves like Tomita-Takesaki, then you will be able to exploit the properties of this theorem. What I mean is that you will obtain what is the J operator for those states and that region. You will get the modular operator in the sense of a full modular Hamiltonian instead of just the modular Hamiltonian of only one side, which is a better defined operator. And then you will be able to guarantee that this operator that you have found has a good modular flow. I'm getting ahead of myself, but this is the punchline. We were going to map the TFD constraint. We were able to map to create an excited TFD constraint, and then in this thing that I will going to tell you for the next 40 minutes, how you map this into a Tomita-Takesaki setup, and then how that help you to find the modular Hamiltonian for this. So a little bit of background. The importance of modular Hamiltonians in general and in various areas have been, I don't have to tell you about this because for the last decade, it's been a very intense research area. So it has been used, for example, to demonstrate these A-neck and Q-neck conditions by Faulkner and company. It was very useful to study these changes, differential changes of entropy via the first law of entanglement. Also, in conmatter and stat-phys, they're being used to diagnose topological states and operator content of the theory. And more similar to things near ADS-CFT or gravity in general, it has been used to prove the Bekenstein bound, to find linearized Einstein equations from entanglement relations. And something that we will make contact with near the end of this talk is also this JLMS proposal stating as an operator equation that there's a relation between the CFT and bulk relative entropy. But everything here is done mostly for vacuum states, which we will try to deviate a little bit from. For excited states, we have found that not that much is.
Excuse me, or
yes.
I see there's a question from Shiran Singh. Please ask the question.
Okay.
Can we move to the previous slide?
Yes.
I just wanted to get some more clarification about linearized Einstein equations. How modular, meaning what does linearized Einstein equation mean? How does modular Hamiltonian help to get some excited?
Yeah, I wouldn't say strictly modular Hamiltonian, but I would say that you can, by using entanglement in the CFT, you can see that you can reach this, you can reach the linearized Einstein equation. So in a sense, that you end up understanding that maybe gravity is emergent from these entanglement properties of the theory in the boundary. But at least that is my way to understand.
Yeah. Maybe I'm getting off track, but I just wanted to know something. What does linearized Einstein equation mean? Is it some sort of perturbation theory of the background?
I'm sorry, I cannot hear you very well.
Does linearized Einstein equation mean some sort of perturbation theory in the background metric?
Yeah, maybe I'm just going to restate what I just said. This is just a way of trying to understand whether you could actually see gravity as a dual theory of a theory. If you have knowledge of the entanglement of the theory, you can using perturbations. Yeah, maybe it's a perturbative approach in that sense, but maybe, yeah, I'm not that keen. Yeah, I'm sorry, I cannot answer you better than I already did.
Okay, thanks. Sorry for the interruption.
No, it's okay, no problem. So, is there any other question? Okay, I move on. If someone asks, yeah, please ask questions. I may, as has just happened, may not be able to answer them satisfactorily, but please ask questions. So for excited states, less is known. We have found these three papers by Lashkari in 15, which using some replica trick, trying to deform this replica procedure, he ends up obtaining these expectation values in the CFT. There was also this work by Sarosi and Ugachin, where they describe excited states, but in a more CFT CFT formalism way, in the sense that you apply an operator to the vacuum and then try to understand how these excitations go around in the CFT. And there is also this more algebraic quantum theory approach by Lashkari et al., which we will make also contact later in this talk. But there is also another paper that is important to us, which was published by Parikar and Balakrishnan earlier this year, just I guess like 5 days before our paper, in which they also study very their setup is very similar, almost identical to ours. They were also worried about trying to understand which are the modular Hamiltonians for these states. They end up getting an expression which is similar to ours, but via CFT, exclusively CFT, a more CFT approach, trying to do a resummation of an expression that we'll get to, and they get that the corrections, they get a perturbative expansion, they get these corrections to the modular Hamiltonian, which looks like this, and it boils down to find this F, which they found. There's an expression. You can look that up in their paper. So maybe I will, regarding this paper, I would say that it's our approach. I would say it's complementary to theirs. They try to do one thing, and we're more focused on the algebraic quantity theory. Try to pose the problem in that language and try to solve it also in that language. So for a more rounded introduction to it, I would say that a modular Hamiltonian of a region A, let's say we have a quantum theory, you have a region A, and we got a state E. So at least in the formal sense, getting the modular Hamiltonian is the same as getting the density metric. That has to do, it's determined by the region and by the state. You just take the minus logarithm of this and you get the modular Hamiltonian. But you can see that taking the logarithm, in general, taking the logarithm of an operator is not something that it's easy to do. And in general, examples have been found. These modular Hamiltonians are non-local in general. They're very complex objects. I wanted to stress something that is something formally important, that for the modular Hamiltonian of a region A, written like this, there's no information beyond A. If you specify A, the operator algebra inside and everything, and the state, you can build its modular Hamiltonian. Actually, it's not only dependent on the region A, but actually it's causal development. But what I mean is something that will be clear in a second. That for our purposes, we will usually build the modular Hamiltonian of A by thinking it embedded into a bigger theory, and thinking of A as a sub-region of this bigger theory. We will build something that we will call a global state, let's say omega. We will trace. You can also build this thing in this different setup of the modular Hamiltonian or the density matrix of the object as tracing on all the other degrees of freedom that live outside this region A. So as we have defined this object up until now, this object is quite ill-defined in the sense that when you compute the BEP of this object, will be the entanglement entropy of the region A. You will get divergences that go with the area of this region, and has to do with the thing that when you cut a thing, as in the expression before, if you trace over the other degrees of freedom, there's some high entanglement between these degrees of freedom, and this will be very badly divergent. So very few pieces are universal, and you have to you do not simply compute and get a number. You have to do some fine-grained study of whether there are universal quantities or not. A more formal and regular related quantity is the full modular Hamiltonian, which can be obtained via the modular operator of the Tomita-Takesaki theory, and I'm going to introduce this right now. But for let's say for having more intuitive understanding of what it is essentially, let's say, the modular Hamiltonian of A minus the modular Hamiltonian of A bar. And in a more familiar setup, let's say I'm working with a Rindler setup or a black hole. The modular Hamiltonian of one side will be the boost operator in one of the sides, and this full modular Hamiltonian will be the boost operator, but globally extended. So this is something like, instead of this upward entirely upward evolution, I'm working with this like this sort of a fan, like in one side moves upwards and the other one side backwards, and that would be the full modular Hamiltonian. So how do we build? I talked about this operator delta. How do we find that? So suppose we start from a cyclic and separated global state, which I'll talk about this in a second. One can define if one can find an operator S which meets this equation, then you can see that the operator S decomposes in a unique way in this operator J and delta. J will be the modular conjugation and delta will be the modular operator. And by a property of J, I will talk in a minute, it's anti-unitary. So you can use, by having access to S, you can do this operation to S. S dagger S will give you delta. And delta is the operator that I talked to you earlier, it's the full modular Hamiltonian. These are properties that you can show if S meets this condition. Oh, I'm sorry, OA, it's any operator inside the algebra of the region A, and A prime is the converse for the outside region. And these properties have to be met by the state. Let's say this is the property that proves that this operator is the state is cyclical with A. And if you can prove that the state is cyclical with A and cyclical with A bar, you can show that the state is cyclic and separating for region A. One thing I think I have not mentioned that I want to emphasize is that S depends, S has the information of the modular operator, and as before, S is both dependent on the algebra that you chose and on the state omega. So these some other properties. One can, if one have access to delta, one can go back to the original object we defined, the modular Hamiltonian of A, by taking trace, and that's okay. And J is an operator, it's the modular conjugation, and takes the algebra object from the algebra A and takes it to A prime, and takes object from A prime and goes to A. And J squared, J minus 1J, which is the identity, is also J squared. Something else I wanted to mention is that both delta and J are operators that cannot be localized either in A and the complement region. They are operators that act on both spaces simultaneously and cannot be disentangled. So as I mentioned earlier, the advantage of putting the problem in this language is that if you can find this operator, you can demonstrate that your state is cyclic and separable. You can reach delta, and once you reach delta, the power of the Tomita-Takesaki theorem will already by itself prove that you will have, by this object exponentiating as an S, you can move this operator from this region to any other side, to any other point in the inside the causal development. So you've reached the good modular Hamiltonian for this operator. Okay, so yeah, I think that's it. So now we reach a point where I will try once again after this introduction to give you the key idea of what we've done. We will consider a particular family of excited states, which we will manage to map to a TT scenario with the guarantee that we've met this hypothesis of the theorem. So if we can do that, we can obtain the modular operator directly in this TT formalism, which is well defined from an algebraic quantity theory perspective and provides a good modular flow automatically. You don't have to prove it like an extra step. We will also identify J, for example, if we'll do some density matrix computation in terms of path integral, we will see that we are oblivious to, we'll be oblivious to the J operation, whether it gets modified or not. So we will be able to answer that question and clarify the TT structure of these states and regions. And as a bonus, these states that we'll be able to map to a TT scenario are interesting on their own from the ADSC considerations because we will have a map for them both. We'll be able to do some computations in the CFT and try to also do some computations in the ADS side. And okay, so there is this interesting, we can map back and forth these two scenarios. Okay, so now let me describe the regions we're going to work with. These are very simple, comes in two flavors, but mostly it's the same setup, just understood differently. So the first time, and maybe the most interesting thing to have in mind, is the Rindler-like splitting. Let's say I have a full theory and I split my system in two, in half at x equals 0. So I can both think, I will be able to think in a sense of the complementary region A bar as a Euclidean, half Euclidean evolution from A to the other side. The modular Hamiltonian in this case is known by the Bisoniano which one theorem. And the other setup, which is mostly the same, but maybe it's not one may not be used to think of it as the same system, is grabbing any system A, and instead of purifying by completing the space as I did before, I grabbed A and put, okay, this is the whole theory and A is just a subregion. I will instead do a purification of A in terms of a copy of A, and this is just like a different way of. I would say that the first scenario is a particular case of the second scenario, but it's mostly conceptually the same. A black hole is also, like, say, a BTC black hole or any black hole is also an example of what I'm talking about. So these two flavors, if this we'll be assuming that the vacuum modular Hamiltonian is no, and if the vacuum modular Hamiltonian is no, we will be able to compute the excited modular Hamiltonian for this family of excited states. So enough about talking about these excited states without describing them. So let me be concrete about this. What are these excited states we are dealing with? These excited states are this type of particular deformation of Euclidean path integrals states. Let me keep it here upward. Let's say phi is 0 here. So what I'm doing is a half an Euclidean path integral from minus infinity to some configuration of fields a sigma. And if this thing is no longer here, one would argue that this should be the vacuum state of theory. It's just the integral over the variables. It's projected on a particular basis element, but one essentially is integrated e to the minus s, so we will get to the vacuum. This deformation has a single trace operator. In general, one can grab any operator, but for the ADS-CFT setup we're going to build, this will be some sort of single trace operator that maps to a single field in the ADS side. This phi in the usual language will be a source and the boundary condition for the ADS fields, but the important thing here is that phi will turn on adiabatically at some point in the Euclidean evolution, and then turn off again, so that when one reaches the t equals 0 region, one can try to describe this theory as some sort of this thing as some sort of excited states of the original theory. We'll maybe can relax this condition, but just to make sure that we're doing things right, maybe this is a useful setup. And by the usual, let's say this is in the CFT side, and by the usual ADS-CFT map, one can map this path integral, this state, to this other state, which is also a Euclidean path integral, projected this time in this field configuration phi sigma, from minus infinity to phi sigma. And now one can see that the ADS setup changes this deformation of the action of the theory into a deformation of the boundary conditions of the integration element. So let me draw this a little bit. Maybe I should have shown this before, but this is more or less a drawing of the procedure I'm doing. This is some deformation, and when one reaches up to sigma, there's an excitation with respect to the original path integral that has to do with this deformation. And let's say I have grab this half sphere Euclidean ADS thing. I will, if I integrate without any sources turned on, I end up with a vacuum at sigma. And if I deform this by these boundary conditions, I will probably excite some normalizable modes inside this bulk, and what I will end up once again with a perturbation at t equals 0. And one, the statement is that this excitation is dual in the boundary, this point like here or any point here, to this excitation that I created here, with this same method. So different, yeah.
Sorry for the interruption. Can we move to the previous slide?
Yes.
Sorry, it seems like the internet connection is very weak. So maybe Shriyanash, maybe could you just write down your question in the chat, and then maybe we can read it at the end, because it seems like your internet is cutting very much.
Yeah, sure. Thanks.
Yeah. I can see that you wrote something in the chat. Also, maybe if you like, we can discuss later. If I have no problem answering, but maybe I do not hear you right, so maybe I'm not. I will not end up answering other questions, something else. Yeah. Okay. Thanks. So okay, but please do not forget your questions. So okay, this is just a different way of writing this. I just gone instead of a path integral language in the CFT, I'm writing it as an interacting picture sort of way. This will be a little bit more comfortable for what we're going to do. And in bulk ADS, I haven't done anything yet. But if I take this large unlimit on the ADA side, also in the large C CFT side, I can, instead of do a path interval, I can just compute this. It will be, this wave function will be very well approximated by this cell, which is the on-shell action, and this on-shell action will depend, of course, of the element on the basis element that I chose, and also on the function. So this is something that will be more comfortable to compute. Okay, so this is okay. Let me comment on this. So now I have already presented the type of states we're going to deal with. I'm going now to make some comments on this formalism that we've learned. So first, let me say that if you start with this expression and write this as a free fields, let's say I don't have just one scalar field, but many fields, but they are at least free in the first order. One can see that the deformation of putting a source here on this element in the free theory limit, it decouples. You can write your field as a field plus some field upsilon. I don't know how this is pronounced, but let's say that this field upsilon is the one that meets the boundary conditions, and then you have like a free. You will have again a field that has to do with the fluctuations with boundary conditions, with zero boundary conditions. So you can end up cleanly rewriting this state at this expression, which is formally a coherent state, and you can compute which is the expectation value of pi and the expectation value of phi. So this slide is to argue that these states in the large limit will become a good approximation of coherent states in the bulk. A different but equivalent way to say this is that one can use a more operator map between the CFT operators and the canonically quantized operators phi, etc. in ADS by taking this, which we'll call the BDHM map, following Harlow and Stanford, this paper here. And this thing that I just told you, a different way of putting this, but an equivalent way of putting this also, is that you can directly in the larger limit canonically quantize these fields, and you can associate the ladder operators that come from this canonical quantization to operators via a particular limit. Doesn't matter, but essentially what you get is that these single trace that these operators that are associated to single fields in ADS can be approximately expanded in the ladder operators of the ADS side. So if we go back to this expression of the state, you can see that one can also interpret this states from the CFT side as coherent states in terms of these excitations O, where these lambda n eigenvalues of this state can be explicitly computed, and has to do with two things. First, with geometry, it knows about the ADS solution inside the bulk. It has some information that has to do with here, and of course has to do with the source we have put. It essentially ends up being a Laplacian transform of phi plus some coefficients that has to do with the solution, with a particular ADS solution you have filled the CFT. So final comments on the holographic excited states. Once one add 1/n corrections, the coherence breaks. You end up having you can see this here. If you are not exactly at n equals infinity, you will get correction here in terms of a square, a dagger square, and higher powers of this. So you will end up more likely at 1/n, for example, you will end up with squeezed states. But if you keep on adding 1/n corrections, coherence will break down. So these are not by construction coherent state, but just in the larger limit, they are a good approximation of it. This state have also an entanglement entropy capture always by classical geometry. For these states, you compute the entanglement entropy, and you can always find a classical configuration that meets that reproduces their entanglement entropy. They have been shown also to be a basis for any near ADS spacetime. And one could also argue that this work sort of as generating states, in the sense that one can try to derive one time with respect to lambda and end up with an approximation of the one particle, two particle, and n particle states. I will take this with a grain of salt, but for maybe for an easier way to compute something that has to do with one particle, it would be something useful to study. So why do we care about these states? So why do these states are useful in this context? This will have to do with the way this excitation work, and the way this has to do with this TFT can be written in two ways. So one can think of this state phi0 that we're going to create as a TFT state of a vacuum state of a single theory, doing, for example, this Euclidean path integral. Let's say that here begins the real-time evolution. And one can think of two ways of doing this. The first way will be like a Euclidean path integral with a single time that goes all the way upwards and evolves up until t equals 0, tau equals 0, a moment of time reflection symmetry. And an equivalent way, which is implicit in this usual way that one is writing it, is to think of it as this will be like a global evolution, but one can also think of this as a local evolution on a maximally entangled state. This state I cross I, it's a maximally entangled state, and this can be rewritten in terms of a local evolution on either side. In this Rindler setup, I wrote this as HR and HL in order to make it simpler, that you will get this exponential right. But for this Rindler setup, this is also the modular Hamiltonian of each piece. And one can also write this as a Euclidean beta over 2, which in this case with beta will be 2 pi. It's just a I pi evolution in Euclidean time. And there is also a key property of this state, that you can both operate with U0 on the right-hand side or on the left-hand side of this Hilbert space splitting. So by the way we have been describing these excited states, the excited version is once you've written this, the excited state prescription for this type of excited states, it's immediate. Instead of describing them as a Euclidean evolution over a single system, we are equivalently able to write this as an operator that acts only on one side or the other side. There are two ways, equivalent ways of writing this. And this will be key because this structure first it makes it very easy to prove that this excited state is splitting and separating. It essentially boils down to because one can move one of these things around, you can easily show it based on the splitting and separating nature of the identity state. And on the other hand, well, okay, it will have some other consequence that I will explain later. So let's begin with a non-Tomita-Takesaki approach to this thing. Let's try to find this the modular Hamiltonian of these excited states. And one can see that U lambda is written like this. It's just a deformation of the K0, the K0 computation. And at least formally, one can write the density matrix for A. One just takes the trace of a bar, and by this property, one can move everything to the A space, and this trace on the A bar region makes it's an almost trivial computation, and one is left with an evolution from minus beta/2 to beta/2. This everything. I think I missed an I here, but it's just the full Euclidean evolution. Notice that here it's just half an interval, and now this you have done the full circle. And this is very nice and dandy, but notice that this is something very non-trivial computation to make it, because one has at least in this stage of the computation a path interval here, which makes this logarithm. It was already difficult to take, but now it's very hard to take. One example that one can explicitly solve is take a generic lambda, but instead that it does not have a tau dependence, and one can check that this computation can be easily be made, because the path ordering becomes trivial. Now one can freely take the logarithm, so one ends up with a concrete result, but for a very simple setup. We have to simplify the problem too much, maybe. One thing that one can think of doing this, starting from this result, is also, as I told you, take, for example, the one particle example and define it this way, and n particle again with a grain of salt, but the n particle should, at least in some sense, look like something like this. And because we are dealing with Rindler like regions, one can also think of mapping all this stuff that we've computed to a ball, and try to understand which is the modular Hamiltonian of the ball in this setup. This is of course exclusive to CFT theories. So let me now, at least to some extent, to meet what I promised you, is how to relate CFT and Tomita-Takesaki. So what I will do now is to, instead of, I will describe what I mean by what I meant at the beginning with a TFT constraint instead of a TFT purification or TFT something. I was talking about a constraint. I will see how this TFT meets Tomita-Takesaki. This make them related. So the usual way one is used to write this TFT state, it's like this, and one usually defines one can define the state like this, or maybe with Euclidean evolution that I described a little bit ago. But an equivalent way of defining it is by via a constraint, which can be written like this. Let me be more graphical about it. Let's say I can define the state doing the following. Let's say I have this state, and I will ask the state that for any operator in the theory, local operator in the theory, I can the operation of acting with an operator on R must be the same as operating with this operator, with the equivalent operator on L. But before that, I move to the left side, then I operate with phi L, and then go back to the right side. So these operations, if I ask for any operator of the theory that these operations are equivalent on the state phi 0, this completely constrains the TFD operator to be of this way. So we will, what I'm going to tell you is that we will prefer for our construction this definition of the TFT vacuum, which looks like a constraint. And we will prefer this one because it is, once we have understood that this is a good definition of the TFT state, this is immediate to map to the Tomita-Takesaki equation, which I now written in this language of two spaces, but this is essentially the same that I have written at the beginning of this talk. Notice that there is a dagger here, but our fields are Hermitian, so this is essentially phi r, and this is phi r again. And by doing an explicit map, I will not bore you to death with, there are some few algebraic steps, but one can show that S0 can be found. S0 has again this structure, and this structure is, of course, this is just a check that everything is okay. One can show that phi 0 has this form, which has already been proven to death. And also one can find that J0 corresponds to the tilde operator of the TFD, which is also well known. But if you've been following me by now, then it is trivial to do this. Well, okay, yeah, that's what I just told you. The advantage of this is that delta is now something that by force will do a good modular flow inside the cone, and also we have found J0 with the path integral method we did before. We were mostly oblivious to this. One can come back and compute the raw R in this language and everything. But the interesting thing is that if you've been following me up until now, the excited version of this must be very easy to make. It's just replacing 0 by lambda everywhere. So one would do something like this, and one can then define a different state in terms of this constraint. So I will make a comment here that may not be clear now, but feel free to ask if you want. One can write this new constraint, and if you start from this constraint and think of it as defining the state, then you can easily map the problem back to Tomita-Takesaki and find the delta lambda and everything. Maybe curious, but perhaps different, is that to think that you can start here and map the problem to Tomita-Takesaki, but it may not be obvious to understand whether this second condition can be proven in terms of the vacuum condition or not. Okay, I'll move on. Maybe it's too complex for us all. Let me move on. So what I was telling you now is, if you follow me by now, the excitation is trivial to see. It's trivial to make. One does this and then follows the map. The demonstration follows in an almost exact way from the vacuum. One is just replacing with delta and taking care of the order of the operators and stuff. But one can find that one can once again find this S lambda. This S lambda once again splits, but there's a very non-trivial result here, that is that J0 is not modified by the excitation, and this is something that was very interesting for us. It is a consequence of the excited states we are studying, being able to that the excited states we are building can be either constructed with operating on just one side or the other, and we can move this around. So this automatically puts your excitation is something that is called a standard cone, and the standard cone excitations are known to preserve the J operation. But once again, from the just density matrix computation as a path integral, one is oblivious to this structure. So we find this a very interesting result of trying to put this into more algebraic quantitative theory, or let's say Tomita-Takesaki formalism. So we have two results here. First, we have this delta operator confirmed that it is a good modular flow. And second, we have what is the J for this excited state, which is the same as in the vacuum, by the structure of the specific structure of the excited states we are looking at. One can rewrite as a path integral the density matrix we are obtaining. Delta is this once again, but now one can see that maybe the CFT computation, explicit CFT computation, will get somewhat complicated. And we will now go to the ADS side in which we already saw that this theory deformation becomes a boundary condition deformation, and one will be something like this. This is the boundary CFT. This is open for pictorial reasons, just to make clear that there is a basis element phi plus that I must insert here and data. So there is, for this computation, there are three boundary data, which is the phi plus, the phi minus, which are the mouths of the Pac-Man, and then you have this boundary information, which has to do with the excitation, where you put the lambda information. So from now we'll deal with this computation and try to see what can we find, mostly in the large N approximation, where this becomes just a on-shell action. Okay. So we're almost, I don't know, how am I doing with time?
Oh, you have plenty of time, but I think it's like 10 minutes. So with extra.
Great. We're almost there. Okay, we're almost there. So let me mention again to you that we could in the large N decouple the boundary conditions that appear here. That one will have to do something complicated. If we take in the large N limit, the fields become free in the ADS, and one can split and decouple the boundary conditions deformation from the fluctuations. You can write the field like this, and this has some interesting consequences on the modular Hamiltonian structure, because you can see that in this approximation, let's say for ADS Rindler structure, as the boundary conditions decouple, the modular flow ends up having a canonical transformation structure in the following sense. The state becomes a displacement in terms of this parameter lambda of the vacuum that can also be written like this. So you canonically quantize the fields, and this D operation is very well known for these ladder operators. They just displace the operators in terms of parameters that once again one can easily compute. So the modular Hamiltonian has these forms. Just the excited one is the vacuum one, just with this F displacement of these operators. So in this case, if we assume that we are in a free theory in ADS, the original modular flow would look like something like this, and the excited state, the excited one, will look like explicitly like something like this. Once again, we can, using these tools and these results, we can compute the modular flow of the fields. They will have this structure, and this structure, once again, is something that we can compute in the bulk. One can confront this with the results from Lashkari in this paper, and we see that it matches, and in the next slides I will do like an explicit computation when I will show you which are the Fs and stuff, but the structure is mostly the same. Most importantly, this structure is something that one can confront with the results found in that paper, where phi n here are the eigenvalues of the Klein-Gordon operator for the scalar. Most importantly, by using the BDHM map I talked to you about earlier, one can also claim that one can extrapolate from this modular flow, the modular flow in the CFT, by trying to do the same extrapolation map. In the sense that one just grabs the subleading order here with u to the delta and try to see whether one can make claims in the CFT by doing the ADS computation. Okay, so one reaches some, if the result in the bulk is this, one would reach a result like this. For a very concrete example, one can grab ADS3 written in this Rindler-like coordinates. One will have this right and left regions. One can explicitly compute the eigenfunctions, and the eigenfunctions look like this, where f is the solution to the radial coordinate, and you expand in plane waves. The n will be something that makes these modes orthonormal. This is very, very standard. And one can compute, for example, this O, which I talked to you earlier explicitly. I will not bore you with definitions, but alpha and beta are functions. Alpha is a polynomial in general. Beta has some poles, but this is the contribution that comes from the pure evolution of the field, from this contribution, from the canonical quantization of fields. And this other contribution is in the second line. Notice that is the one that is proportional to lambda, whereas this is just a pure canonical quantization evolution. And you can see that because this epsilon parameter is nowhere to be found here, and this is in front here. And you can see also that for s equal 0, this vanishes. So this has the correct structure, and one can put numbers here and compute things. One last thing before we wrap up is that we can also compute in this language modular Hamiltonian expectation values. By looking at a JLMS equation of this structure, we will not make any claim with this first operator, but one can see that by exciting things with lambda, let's say with a scalar matter will appear here in the modular Hamiltonian bulk region, bulk contribution. And if we are dealing with the formations of the metric, maybe something will appear here. And the structure of these elements by the matrix elements of these operators can also be described in a very, at least formally in a very simple fashion. One computes in the semi-classical limit. The solution will have this structure where this is the extrinsic curvature of the different regions that contribute. And as for matter, when we have a contribution coming from sigma plus, sigma minus, and also from this boundary, where this pi plus is the conjugate momentum to this region, will be the formal conjugate momentum with time in this angular variable, and this is the contribution coming from the excitation. This will be something that will always be present, and when lambda goes to 0, this contribution disappears. And the field structure of this, the solution, the classical solution, will be something like this, where these phi plus and phi minus are bulk to boundary. I'm sorry, bulk to bulk correlators that are become 1 at phi plus and 0 at any other boundary. So this is a bulk to bulk correlator that has this particular property that is 0 not only at the asymptotic boundary, but it's also 0 at phi minus. Phi minus is the converse for phi plus. And this is also a bulk to boundary correlator, but this bulk to boundary correlator has to be forced to be 0 at sigma plus and 0 at sigma minus in order for this to have the correct structure for all the boundary conditions one has to do. This looks somewhat tedious, and I can confirm you that it is because we made the computations. So, but one can find in this simple ADS3 Rindler example the explicit the explicit form of these correlators. It's just an expansion in terms of sine and cosines and stuff. And one can, for example, compute this modular Hamiltonian excited modular Hamiltonian matrix element that has lots of contributions, but mostly the most important note is that once again there is this epsilon that from which we can trace which are the contributions that come from the excitation. This is this first one, the second one. This is just a normalization thing, and the most important terms of I think this one and this one and this one that mixes things that have to do with the boundary with things that have to do with the element basis we have chosen to project onto. This is very numerical, but the main point of showing you this is not for you to see that we've made some computations, but just to see that up until now the talk has been a little bit only formal, and I wanted to show that you can actually do computation and compute matrix elements of excited modular Hamiltonian explicitly and associate the numbers to it. So let me wrap up. As conclusion, we've introduced some modular Hamiltonians. What are modular Hamiltonians? What are the importance in different areas? We have also introduced some Tomita-Takesaki elements. And by now I've probably emphasized more than enough that why do we care and why did we wanted to put this in Tomita-Takesaki language. We have also described maybe something very simple, but we have not found in the literature this relation between Tomita-Takesaki and TFT beyond the vacuum state. We have described this holographic excited state and why do we think they are useful. We have found some CFT results, but mostly formal results, and we have been able to go beyond in the large limit, at least in the ADSI. We have managed to go beyond and use this BDH map to come back to the CFT with our results. So I think that will be it. Thank you and stay safe. Okay, and this is where I am now. This is the old ISLP that we have been working for I think up until the last 3 or 4 years, and this is the new one which is just been built. So yeah, thank you very much. That's it.
Thanks a lot. So I guess everyone can unmute, and there's still some time for questions.
Maybe the person what was doing questions before can start doing them now if they want. Let's try to probe the make once again.
Okay. Yes, please. Shuriya Nash, can you ask a question? Yeah, okay. Just unmute yourself.
Thanks a lot for the talk. Maybe my questions may be slightly tangential from the exact talk, since I do not have a very good formal knowledge of modular Hamiltonians. I just wanted to know what does the modular parameter S mean? Does it give a unitary evolution in the modular space?
Okay, let me restate your question, maybe if I got it right. You wanted to know more about what this parameter S is?
Yeah.
Is that your question? Okay, so let me go.
Yeah, yes.
So one traditionally thinks. Let me answer something. If it's maybe too basic, let me move forward. The thing is that this delta operator is via this evolution is telling you how do I don't know if this is a correct, a very formal answer, but at least for me, it's this delta operator is showing you how your degrees of freedom move when you move inside this causal development. You know that the information on A should not depend in a Lorentz invariant theory of whether you have chosen a specific foliation, for example, this one, but maybe any other foliation inside this causal development should be equivalent. Will have the same information. So you should be able to freely move inside this cone without losing anything important. In that sense, I have chosen to work in a specific foliation where all this region A is t equals 0 region. But then I should be able to recover like the whole causal development because I have made a choice. So this S, I think of this S here used exponentiated with this operator as a way of recovering this thing that we already knew, that that the expectation. Here I'm writing this as an operator equation, but if one takes the expectation values here, one can show that the expectation values taken at t equals 0 and at any other S are the same, which would be I think more in line with what you wanted to know. this operation, the important consequence of this operation is that by you can freely move S forward and backward, and the expectation value of the operator will not change. So what you're recovering is what I told you, that you know that using this region, you should recover all the information inside the causal development. There is nothing that can happen here that you could not have predicted if you have all the information in A. So I guess my answer is, what is this S? This S is something that will, with the aid of delta, will aid you to move inside this causal development. And the importance of this symmetry is because it's stating in a very mathematical, precise way that if you know the information in A, you know the information in all the causal development of A.
So if S is like is it like the evolution time which we use in the unitary picture, meaning is it just like the time we evolve unitarily in quantum mechanics?
Yeah, it's not a time evolution.
Is it something different?
Yeah, it's not a time evolution in the sense that, for example, information in A, let's say you have information in A here near the boundary, and this information I can grab a laser and turn it on, and information in A escapes, like the time evolution of this photon that emerges from A can escape the causal development. So the time evolution, for example, of that light ray can escape the causal development of A. But so for example, you can see that by unitary time evolution of something that goes at light speed away from A escapes this causal development. So unitary evolution will take you away from here. But if you start with information in A and evolve with this modular operator, you will always move inside this cone. You do not escape the cone. But there are things that can happen in A that move away from the causal development of A. Am I making myself clear?
Yeah, I think, Pedro, I think that's clear. Let me just maybe stop here, and then if there is more questions, we can make it like an informal discussion after, but I'm going to stop the recording.